Hi, I'm Bob Hughes with JD Squared, and what I'd like to talk to you about in this video is the MAD series of CNC cutting tables. Every manufacturer obviously is going to tell you their machine is better, and we're no different. So what we're going to do here is we're actually going to show you component by component the decisions that we made at the time. We've been working on this for a little over 3 years, so obviously we made a lot of those decisions. We're going to start off with the base component, then we'll add the beams, etc. And by the time we get done, we'll have a complete machine, and you'll know why and how we built it. So without further ado, let's get started on that. Okay, first up, what we have is the base. All MADs are available in a 4 foot by 4 foot, 4 foot by 8 foot, and a 5 foot by 10 foot configuration. They all will handle steel plate up to 2 inches thick. That fact, combined with the high rapid speeds that are achieved with our brushless servo drive system, indicated very early on that a bolt-together frame was not going to be sufficient. What we decided on was a completely welded box structure. We make the main box out of 3/16" steel plate. We support it on 4-inch by 3-inch 1/4-inch wall steel legs with 30mm leveling pads underneath there. In order to handle a little bit more weight, slag, etc., we've also included cross braces underneath the table. That allows you to pick the machine up with a forklift and we can't damage the table. We have sufficient strength built into it. Since the machine is designed to handle such a heavy thickness of plate, we also supply the floor retainers. And what these do is once you have the machine in position and leveled, you can install these around the feet, and that way if you bump into the table or something with a forklift, these will help restrain the table in its current position, therefore not knocking the thing out of alignment. All right, why don't we move on now to the inside of the box. Okay, inside the box here, the first thing we're going to show you is, if you notice, there's a hole cut in the bottom of the machine right here. What that is for is so that you can easily clean the slag out. By simply sliding a metal 5-gallon pail underneath it, you'll be able to just scoop the slag right into the pail, take it out, empty it, and off you go. Pretty simple stuff. Now let's talk about the slat mechanism. We've been using water jets, lasers, plasma cutters, everything for a lot of years, and we made a list of things that we wish we could have in those machines. We've incorporated everything we could think of into this machine. One of the features we wanted was to be able to adjust the slats up or down. So let's say later you want to convert this to a water table, you may want to be able to adjust the slats down so that the water level will not, roll over the top right here. Now let's say you're loading heavy plates. You may want to adjust the slats up so that they're even with the top so that you can easily slide the plate on. All that has been incorporated into the MAD bases with a simple adjuster bolt right here and slotted slat retainers. You can pretty much adjust it any way you want. Now let's talk about curves or straight slats. If you're loading heavier material, a straight slat is the way to go, just because it's like a sled. They just slide right in, they drop down. If the slats are curved, you end up with a little bit of resistance right there. However, if you're doing some strange shaped parts, you may very well want a curved slat. So what we did was we designed it so where that the slats are reversible. That actually gives you 3 different ways to mount your slats, either straight, half-arced, or full-arced. And a full arc would be a 2-inch spacing between them, 2 inch in the middle of the arc, and then a half arc would be 1 inch. We did all that because just to make it a little bit easier, where you get to decide how you want to put the slats in, not us. All right, let's move on now to the downdraft air system. Okay, let's talk about fume management. There's 3 ways to accomplish this. The first is the easiest, and it's just don't handle the fumes at all. Now, if you're dealing with a plate that's relatively clean and oil-free, then it's actually not as bad as you think it would be. Now, the other situation is if you're doing a lot of cutting. In that case, you're going to either want an air downdraft type system or you're going to want to go to water table. Let's talk about the air system first. What we have right here is the optional air box that we could supply you that bolts to that opening that you saw earlier right here in the floor of the table. It incorporates a 6-inch outlet right here that you could easily hook into a blower system. Also has a door on the front so that as you scrape the slag into it, you can still easily scrape the slag out of this without having to get into the machine too much. Works pretty well. Doesn't work perfect, but works pretty darn well. Now, let's say you're doing a lot of cutting and you're really trying to minimize the amount of dust and stuff like that. You're probably going to need to go to water tables. At JD Squared here, we prefer the air downdraft system just for two reasons. One, a water table are notoriously difficult to clean out, and the other factor that people don't realize is that when you use a water table, your metal will rust if you don't thoroughly clean and dry it upon taking it out of the machine. So we're going to leave this choice up to you. Having said that, if you decide you want to go to a water table, what we do on the bases is we tape off all the seams around the sides of the edges. And what this allows you to do is you can either take your MIG welder and weld the seams up, or for a nominal charge, we'll do it for you. The main base is actually bent out of a single piece of metal, so you're only welding the sides. You're not doing that much welding. Now, the other thing you'll have to do to turn it into a water table is either buy the cap from us, or since you will now have a plasma table, burn your own, put a little silicone, and off you go. You've got yourself a water table. That pretty much sums up everything you could do to try to manage your fume. So why don't we move on to the next component? Okay, what we have here is the Y-beam assembly. The Y-beam mounts to the side of the machine, runs up and down, and that's what your carriage and your gantry is going to roll upon. When we first started building the machine, we were using extrusions, and what happened was we wanted to know what our cost would be to have custom-made extrusions. So we called up an extruder. He asked me, for that size shape, what kind of accuracy are you looking for? So I told him, I thought, oh, I don't know, a few thou over 5 or 6 feet. He goes, well, sir, you obviously don't know anything about extrusions. Let me educate you. And what he told me was that they define a precision extrusion in that size range as allowable to have 1 millimeter of arc, that's 40 thousandths of an inch, every meter, every 40 inches. Well, clearly that's not straight, that's not precision, so we quickly ruled out extrusions. What we did instead was we decided to go out and buy a $300,000 150-inch milling machine and fabricate the Y-beam out of steel. So we used 4x3 box tubing, 1/4-inch wall with a heavy steel strip welded to the top, and then the feet, of course, on the bottom. What we do is we mill the feet in the bottom in a twist neutral jig so that we don't actually take the twist out. Then we flip it over, check it for flatness, and then we completely mill the top surface up here, and we V-groove the top so that an 1.25-inch alloy shaft will be able to fit into it nice and straight. Since we've also milled this straight, we load up our 3/4-inch spur gear, 16 pitch, which is the same stuff used in like $300,000 machines, by the way. So we put that on top. Now we know that we've got very good alignment with everything. So the question is, quickly, why did we choose round shaft over a linear guide? When you're plasma cutting, you're generating a lot of metal vapor, that metal dust. That dust gets all over the place, gets on your rails, and what happens, it eats away the seals, and next thing you know, you're continually cleaning out your linear blocks. We thought this was not the way to go. Now, if you could enclose them, they're the absolute best way to go, and that's why you'll see them on laser systems and stuff like that, but they're enclosed. My personal opinion is people who are using those, it's mostly about marketing and not about the quality of the machine. We didn't want to do that. We want a machine that you're going to be able to run 24/7, and she's just going to do it time after time again without failure. So what rides on top of the alloys deals? What we did is we designed this this roller, and it uses an 8,900 pound capacity dual row radial ball bearing. Considering it's only carrying 75 pounds, I don't think we're going to have any kind of warranty issues there at all. What we've done when we milled the profile, we recessed the center of the roller so that the roller is running on the outside edges and not the center of the roll. This allows us to be, have a little bit of dust on it without having to worry about the roller riding up and down as she cruises up and down the machine. Then, of course, we have the bumper stop plates on the end to prevent the gantry. This is a very, very fast machine. We really needed a rigid structure, and in order to achieve that, the other advantage of the roller system compared to, let's say, a flat piece of coil roll with cam followers is, since we're touching on both sides of the shaft, we eliminated that side play. That allowed us to increase the rapid speeds of the machine and still retain the rigidity that we needed. Well, that pretty much sums up the Y-beam. Let's move on now to the Y-carriage that actually runs on the Y-beam. We've gone ahead and assembled the rest of the machine minus the wiring and covers so that we could better show you the Y-carriage. And that would be this system right here. It's a steel weldment, precision machined, and the rollers mount to this that we showed you previously. If you can see it in the video, we have cover guards on here to prevent fingers from getting crushed during operation. Let's come over here to the drive system right now. we're utilizing a 3/4 inch face width 16 pitch spur gear. The extra heavy width right there gives us a very long life of the spur gear. If we go up from that, it's driven by a 10-to-1 high precision gearbox, which in turn is driven by a USA made brushless servo motor, NEMA size 34, by a company called Technic. Fun fact, when we were originally designing the machine, our goals were 1,000 inch per minute rapids minimum. The motor turned out to run so good and put out so much power, we're actually able to achieve 1,400 inches per minute. So there you go. Now, how do we engage the spur gear into the rack? There's a lot of ways that during our R&D that we've seen people do it. We've actually built some of them ourselves and tested. Most popular way is you'll see them, they'll pivot off a single bearing, they'll have a spring on it, or some kind of air cylinder. We didn't understand the air cylinder because the spring does the exact same job, much less complex. What we decided to do, though, to maintain a more perfical alignment of the spur gears, we went with twin bearings right here, block bearings, running on 20mm ground and polished rods. And what this allowed us to do was have a system that engaged very vertical. Well, that pretty much shows you everything about the Y-CARRIAGE. Let's move on to the rest of the machine. Okay, we've talked about the Y-CARRIAGE. Now let's talk about the gantry that's bolted to the top of it. To better illustrate its features, what I've done is I brought out a raw machine gantry right here to show you. Well, during the design phase, we have obviously evaluated extrusions because that was the cheapest and simplest way to go, and we quickly ruled them out after testing because of the straightness factor that we didn't like. What that left us was the possibility, or the only option, was actually to make an aluminum weldment. So we did that. Once we designed the weldment, now it came down to how are we going to machine it straight. So let me go through those steps with you to give you an idea how much trouble we go through. First thing we do is we're going to need to machine the feet. So we created jigs that would allow us to bolt the gantry into the milling machines without taking the twist out. We then mill the feet flat. We remove the gantry from the CNC. We check it on a parallel plates to make sure everything's flat. If it passed that test, it then goes into another CNC that we bolt under the precision angle plates, and now we're milling the top surface. This ensures from the feet to the front face here we have 90 degrees. Once we do that, we then reload it yet again, and we mill the spur gear rack surfaces, and this ensures that the spur gear rack is vertical, matching the spur gear on the Y-CARRIAGE. The way we do it may not be the simplest way, but we honestly believe it's the best way. So, having said all that, let's move on to the next components. Okay, let's look at the X-carriage right now. It's really nothing more than a Blanchard ground steel plate that we have drilled and tapped with 8mm holes. That allows us to bolt pretty much whatever we want to the surface. In this case, we have the Z-axis that has been set up for a plasma system. In that configuration, that also allowed us to have 2 docking stations on each side of it because all of our torch mounts are magnetically loaded. So you can literally put one on each side. So if we were cutting with plasma, for instance, we could store an oxyacetylene torch off the side right here for future use and not have to remove any of the hoses. Now, let's move a little bit inboard. First thing you'll see is the rail system. And what we did is we took a page out of water jet manufacturers. 6-figure water jets use 12mm hardened rod running with concave bearings because of the dirty environment. We get the same kind of dirty environment plasma cutter. That's why we don't want to use a linear guide with its exposed seals. So we chose that rod. Moving in a little bit further, we're using the exact same motors that we did on the Y-beams, brushless servos made in America, NEMA 34 size, driving 10-to-1 high precision gearboxes with a 3/4 inch face spur gear. Supporting all that is twin linear blocks, bearing blocks, running on 20mm ground and polished rods. What this allows it to do is keep a very nice vertical alignment so that the spur gears have correct engagement. Now if you look down inside here, you'll see an electrical control board. What it is, we have spent a tremendous amount of effort trying to control high freak noise created by plasma systems. So in order to do that, we have to isolate certain components. This board is one of the first steps on this side of the machine to preventing the noise from getting back to the computer. Normally, in operation, there is a cover that goes right here that will cover all these, the inside mechanism right here. And that's pretty much it for the X-axis. All right, here we have the Z-axis. First thing is the motor. It is also a USA-made brushless servo motor, similar to the others, driving a lead screw, which the entire assembly is now riding on a 25mm linear guide. Remember earlier when I was mentioning I didn't care for linear guides that were exposed? Well, this is the ideal application for a linear guide, because once the cover goes on it and the bottom seals, it is totally enclosed and it allows us very good rigidity and all. Looking on down a little bit further, you'll notice two switches right here. The outboard switch is what's used in the Z homing process when the machine homes when you first start it up. The switch behind it has to do with another function that is the floating head function, and I'll explain to that a little bit more in a minute. Moving on down here, we come to the magnetic base. It has a lever system in it which will trigger off a switch once the torch leaves the machine. So right now the switch is engaged because there's no torch on it. The torch over here is in one of its stations. We have two stations on each side with the magnetics, and if you look on the back of the torch mount, you'll see the magnets back here with the cones that line up here. As soon as we place this on here, if the torch was to hit something on the bottom and move, you'll see the lever actually engaging this switch right here, which will tell the control the torch is trying to leave the building, stop moving. Now, let's go on. We mentioned earlier about this extra switch here. What it all relates to is actually touching off on your work surface. There's three different ways of telling the computer that you're at the correct height, called IHT, initial height testing. The first and the simplest is called an omit connection. When you literally drive the torch down, you touch the bare metal, you create an electrical connection, and the computer picks that connection up and says, okay, we're there. That works great. Now, supposing you're cutting something that is painted and you cannot make an electrical connection. In which case there, we're going to go to the second option, and it's called a floating head. And what will happen is once you touch down on that non-conductive surface, the head will rise up because the motor's still driving the axis down. That will trigger off that inside switch telling the computer that we are on the material. At that point, we now know where to lift up to initiate the plasma arc and start cutting. The other beauty of this here is, let's say we're cutting with oxyacetylene and we got a flame. In the very near future, one of our pet projects will be a probing system that will be able to flick down, and you'll be able to probe off the plate in particular areas. The controller will remember the height, and that way as the oxy fuel torch is moving around, we can actually adjust the Z height on the fly and hopefully produce a better cut. Well, that's pretty much everything about the Z axis. Okay, we finally reached the point where the machine has been totally assembled. All the covers are on, she's wired, she's ready to run. This video has been mostly about the construction of the structure of the machine. We've deliberately left out the electronics, the computer software, the stand, the whole bit, because we need to go into a little bit more detail on that, and it would just make the video too long, so we'll create a second video for that. Last note about the construction of the machine: it has been designed for a world market, not just the USA. Therefore, we've utilized metric nuts and bolts throughout the entire machine. Fairly heavy construction, you can probably see a little bit in the video. She weighs a little over 1,200 pounds. That's a lot of weight for a small 4x4 machine. Anyway, in closing here, I'd like to thank you, but first, let's fire this mother up and cut some metal.
there we go.
Okay, that was pretty simple. What we just cut was some 16 gauge steel at 350 inches per minute. Not much load on the machine, but we did want to show you cutting metal. I'd like to thank you for your time, and don't forget we have the other videos that'll show corrugated cutting, the electronics, stuff like that. But right now, thank you very much and good luck with your future projects.